Alright, so today we're going to be solving some simple trigonometric equations. If you are in my class, you probably want to pull out the handout. It's called like the 14-6 note guide or something. So we're going to do a couple examples first, and these are both examples like the first variety of trigonometric equation mentioned in the handout. I would call these linear trigonometric equations because they don't have things in them like sine squared of theta. They don't have things in them like a theta raised to a power. They don't have things in them like logarithm of sine of theta. Those equations all exist as well. These are just simple linear equations. And I think you guys have known how to solve linear equations. Everybody in here has known how to do that for a while. So what if you were solving for x? What's the basic strategy when you're trying to solve a linear equation like that? You're trying to get the variable by itself. Isolate it. Yeah, get it by itself. Very good. So the first problem, what should we do first? What are we trying to do? We want to get theta by itself. Subtract root 3. Right? Do that to both sides. So then you have 2 cosine theta equals negative square root of 3. Next step, you want theta by itself, remember? Divide by 2. Right? You cannot divide by cosine because dividing by cosine doesn't get rid of cosine. That's not its inverse. If that makes sense. So we have cosine of theta. I like your thinking, Josh. Equals that ratio. And now this should be starting to look familiar. You should look at that by now and be like, cosine equals a ratio? Right, okay, cosine's supposed to be a ratio. That looks like stuff out of the unit circle too, doesn't it? Root 3 and 2, so you should be starting to feel a little confident. The question is, how do you actually get theta by itself? This is like something we did from last time. To get rid of cosine, you use its inverse, which we wrote down as inverse cosine. You do it to one side, do it to the other. It's tempting to think this is multiplication, is it? No, it's using the inverse cosine operation. So I like to think of it as chewing on that. It's putting this stuff inside of that stuff. And when we did function composition, and a function's inverse operation was composed with its regular operation, or vice versa, they always cancel out if they're truly the inverses, right? So then you finally get theta by itself. So the angles that we want to find this answers to this equation are those ones with an inverse cosine of root 3 over 2. Those angles that have a cosine of negative root 3 over 2 are our answers. Now some of your problems are going to ask you to find all the solutions from negative infinity to infinity. Some of them will have a restricted set of places they want you to solve for. So these are both going to be find all the answers. So just like we did from the last lesson, what angles have a cosine ratio of that? I'm not going to guess. I'm going to draw. It says how to draw right there. So I'm going to say, all right, thinking like I'm in the unit circle, where's cosine negative? Cosine was x or y? X. Where's x negative? Here? No. Here? Okay, that's one spot. Adjacent is negative root 3. Where should I put my 2? On the hypotenuse, since that's the way cosine works. What's over here really, guys? 1, my triangle's not to scale, right? Root 3 is supposed to be bigger than 1. It's like 1.7, so my triangle's not to scale. What angle's always across from 1, though? 30 degrees. So 30 degrees over there is one of my answers. So I'm going to say my answers to this problem. I'll write them in red. My answers are, that's pi over 6. But pi over 6 over there is 6/6. Back one is 5/6. Plus 2 pi k, where k is any integer, because any coterminal angle, anything that ends in that same spot, will also work for this equation. It'll also be an answer. And once we start looking at the graphical solutions to these next week, you're going to be like, whoa, there's tons and tons of answers, like tons of answers. You'll see them all on the graph. So that's going to be all of them. All right, there's one other triangle that will also do this on this problem. Where else is x negative? This quadrant and that quadrant, right? So if I draw the exact same triangle down here, also not to scale, how many degrees are in there? Same, right? 30. But how many 6 does it take to get over here? 6/6 is 1. 7/6. So we'll say 7/6 plus any coterminal angle will also solve this equation. If you don't believe it, stick some answers in and try. Let's try it. I'm going to make sure my calculator is in degrees or radians. What do you guys think? What are our answers in terms of? Radians. So this should be in radians. So I'm switching my mode to radians. And I'm just going to type in exactly what we have, but I'm going to use one of our answers. So I'm going to say 2 cosine. What was one of our answers? 5/6 pi times 5 pi over 6 plus the square root of 3. And our answer is supposed to be 0. 0. Let's try another one of our supposed answers. I think 7 pi over 6 is supposed to work too if I plug that in, right? 0. Let's pretend we jacked up and we got, like, I don't know, 3 pi over 4. Clearly not 0. What's one more answer that would work, guys? Can you help me out? We've got a whole infinity of answers up there. 5/6 pi, 7/6 pi. Somebody give me one of the answers. 11 pi over 4? Are we counting by sixths? Somebody else help me out. Or Carson.
15 pi over 6.
15 pi over 6. Let's see. I like it. I can see 15 pi over 6. Can you? He's looking at this one, I think. And in sixths, 2 is 12. 12 sixths is 2. 12 plus 7 is... Now, or were you looking at the top one? 12 plus 7 is 19. You might have been looking at the top one. 12 plus 5 is 17. Let's try either one of those. Either one of those should work. So let's go... We'll go... I think Carson said 19, I remember. 19 pi over 6... Yes! It's totally working. Did you ever guess all those answers without doing this kind of logic or something, you know, another way to do the same thing? I don't think you want to be that old, this young. So, okay. Let's try the second problem. I don't think we need to do anything different. We're trying to get theta by itself. This is like one of those problems when you started basic algebra where you had x on both sides and you did like terms. Yeah? So what should I do first then? If I've got like termy things that are the same. Put them together, right? Like there's half of this thing there, one of these things there. Put them together. Let's subtract. So 1 minus a half is half. That equals a fourth. I want sign by itself though. A couple ways we could do that. How do I get rid of that half? I could multiply by 2. That would work. Or you could divide by a half. I think a lot of people at this point prefer to like divide to get rid of multiplication. Some of them do it that way, okay. If you want to do it the other way, great. So then copy dot flip, right? Divide by a fraction. What's 2/4? So we get sine of theta equals a half, and the new thing that we've been focusing on the most is how do I get rid of sine? Inverse sine. I'm going to use the other notation. Our book doesn't use it. You'll see it is used in other cases though. Another way to say inverse sine is the arc sine. I'm going to do it to both sides. Cancels out. It's just another notation. The same thing. And then we need to find all those angles where we get a sine of 1/2. Sine is x or y, guys? Y. Where is y positive, like positive 1/2? Here? Yes. Sure, that's one place. Sine is opposite over hypotenuse. Which triangle is this? You can put the root 3 there if you like, or you can just be like, all I really care about is the angle. What angle is this? It's 30 again, right? This one's 30. So our answers on this are going to be theta equals, right there is just 30, so pi over 6 plus every coterminal angle that we can count. And there's another spot where we'll get the same sign ratio. Where else will sine be 1/2? Here, here, or here? In quadrant 2, right? And that's because, the way I like to think about it is because y is positive here. So, 1, 2, we're also going to get 30 degrees there. Didn't we just do that a second ago? I think it's on the board still. What's a sixth over here? 6/6. 5/6. And every time we get back to that spot, k is any integer. Okay, so there's how you solve some linear trigonometric equations. Note, you need to know how to do the inverse.
Why do they call it arc sine?
Yeah, that's historical. I can't exactly remember. I think it was because you'd have to think about how many degrees or radians of arc it would take in order to accomplish getting that ratio. So it has to do with people looking at protractors and stuff and finding the exact right spot, the exact right amount of arc on the protractor that it had to do with. There's more to the story than that, though, Mr. Goodman. It's a good question. So looking at the worksheet, guys, and also looking at these second two examples that we're going to do today. Examples on your handout in the second box, and these. What might we call these? What kind of trig equations? Quadratic, because they all have what? Squared trig ratios. Or you could call them, it's another name besides quadratic. Parabolic. Very good. Jacob's got that other. Yeah, that'd be good. That's fine. Okay. So, when we were solving things that were parabolas, usually we resorted to one of two things to solve those equations. There was the big one with lots of little types. Started with an F. The thing that's probably going to be more than future classes than anything else, and that's factoring. And you could also use the quadratic formula. We went over how to solve them some other ways, but those are the two main ones. Kinds of factoring and quadratic formula. So those are the two things that you'll need. Maybe you won't even need the quadratic formula on this first worksheet. I don't think you do. So I think we can do these with just factoring. So when you're solving a quadratic, though, you have to make sure that this side is always 0 first, right? No matter how you're doing it. So I'm going to subtract my 3. Set it to 0. That one's already set to 0. And I'm going to see if this one factors, hopefully. So we don't have to use the quadratic formula. So what do you guys think? Does this one factor? It's like a trinomial. Factors of 3. What are our only options? 3 and 1. Instead of x and x, sine theta and sine theta. And then you say, all right, can I have some combinations of -3 that'll work? I think if I make the 3 negative or positive. And this, there we go. So now when we did a quadratic like that, I think the next step was to set each one equal to 0. A lot of you guys used to like to skip this step, that's fine. But in trig land, I don't think it's so wise to skip it. So sine theta minus 3 equals 0 says sine of theta equals 3 if you solve it for theta, because now these are both linear equations, like the ones we just did. So I've got that one. And then I've got the other thing could also be 0 to make the whole thing 0. Right? So that says if I subtract 1, sine of theta equals -1. So then we try to do both of those. So I'm going to say theta is, if I use the inverse on both sides, the inverse sine of 3, or theta is the inverse sine of -1. Sometimes you'll get solutions from both of these problems. Sometimes you only get them from one. It just depends. Let's start with this guy, the inverse sine of -1. That says, where is sine -1? What do you guys think? Is this a triangle or an edge? You can try to do a triangle, but you won't be successful. Which might happen sometimes, that's fine. It's an edge because sine is the y-coordinate. This is really asking you, where's the y-coordinate -1? Here? Here?
Yes.
No. Nothing's negative there, right? Here? Nothing's negative there. Here?
Yes.
Yes. Making sure this point is really 0, -1. Yes, that has a y coordinate of -1. What angle is down here, guys? 90's up here. It's 270, but we want radians. See, this problem didn't say all answers either. Here's another difference. This one says I only want the angles between 0 and 2 pi. So that one's between 0 and 2 pi. That one is theta equals 3 pi over 2. Thank you, Mr. Lee. They couldn't say negative pi over 2, even though that'd usually be an answer, because negative pi over 2 is not between 0 and 2 pi, even though it's coterminal. Does that make sense? Now, there are other answers for this one. Well, is there a point on our unit circle that has a y coordinate of 3? No way, it's the unit circle, right? Is there a triangle where you're going to get opposite over hypotenuse is 3? You can try. You could try to draw that triangle and be like, okay, opposite is 3, hypotenuse is 1. I don't think we had a triangle like that. And if you remember what we talked about last time, which will make more sense when we get to graphs, the sine function can never have something put into it more than 1. If you put that in your calculator, for instance, it's going to tell you, I'm broken, error. So this just has no solution. So there's no solution that we even need to worry about here. There's no triangle that you can make that will do that. So this is no solution. So we just got one answer on this problem, 3 pi over 2. That's it. Okay, this parabola says we only want our answers, and this time they want us to be in degrees, okay? They only want the ones between 0 and 360, so we'll keep that in mind. This guy, I do believe factors. This is the longer factoring process, so I'll walk you through it. I'm not going to ask people questions. So I think you go 4 times 3 is 12, if it's going to work. Then you say factors of 12, it'll give me 7, 3 and 4, but I want -7. Make them both negative, and that should work, right? So then I go rewrite the outsides. And I'm going to say -4 tangents, -3 tangents. Use that clever combination of the middle. And then if you remember, you play the what they share game. You share a 4 and a tangent. Second two share just 3. We could make that 3 positive or negative. The right answer is negative. You might put it as positive and then have to back up. So what's left if I take 4 tangent out of this? Another tangent. If I take 4 tangent out of that, there's one of those left. If I take -3 out, tangents left. If I take -3 out, 3 divided by -3 is -1. Yes, I know I did my problem right at this point because those match. So then I take that big chunk out, as the two terms, this one and this one, share it. So I'm going to pull it out, write down what's left. Here I have a 4 tangent left. Here I have a -3 left. Now it's factored, ready to set to 0. So I'm going to say tangent -1 equals 0. That's one problem. Notice I'll use little bullet points to separate. I recommend you do the same. 4 tangent -3 equals 0. Either one of these might give us answers. One of them might not work, like the last problem. Depends. So I'm going to say this one says tangent equals 1. Apply the inverse tangent. I'm looking for triangles or points where the tangent is 1. Those points, you might think that those are points. If you try it, you're going to find out that doesn't work. It's best actually to think of this one as 1 over 1. If you've been doing your homework thoroughly, that should make sense by now, but it might not yet. That's okay. So I think that might happen here. What's the angle in there? 45. There's root 2 there. I don't really care about it, but. And then I think that will happen in what other quadrant? I heard it. Third quadrant. So over here you'll have -1 and -1, but -1 and -1 is positive 1. So 45 over there is also an answer. So far our answers are going to be, remember we're in degrees this time, which is weird. Usually solve these in radians. But whatever, they want us to be in degrees, cool. So 45 degrees is an answer. 45 degrees over here is an answer. How do I get 45 over here? I add 180, or you just remember in that quadrant 45 is 225. That's 180 plus 45. Well, let's see if we get any answers for this one. We might. So I'm going to try it. Let's see. Tangent of theta equals 3. I heard it, so you're going to get 3/4. So then tangent of theta equals, use the inverse on both sides. You get the inverse tangent of 3/4. Now, that's less than 1, so you know you're safe. If you remember from last time, I'm sure it's still a little bit vague, but tangent has no restrictions. You can put anything bigger than 1 or whatever into it. That's because its graph has a range that goes forever. Sine and cosine have a restricted range. But this guy is not from the unit circle. If you try to draw this on the unit circle like we just did, and you go opposite, adjacent, that's not one you know from the unit circle, but it is one your calculator can do. So almost all the ones I gave you on that worksheet, if not all, will come out from the unit circle because I want you guys practicing your unit circle. Does that make sense? If you run into one that doesn't, or you're not sure, use your calculator, like this one. This one you have to do with your calculator. So let's turn on our calculator and get it. So I've got a lot of mess here. Let me move my calculator. Okay, so I'm going to let my calculator do the dirty work this time. So I need to tell it to do the inverse tangent. Oh, and was I supposed to be in degrees or radians? The problem told me degrees. I better go back and switch. Inverse tangent of 3/4. It says that angle right there, we'll write it down, is about 36.870 degrees. That's between 0 and 360, right? Is there any other answer? Jacob's like, why would you ask if not? There's one more answer, and it comes from the same thing. This is probably the subtlest thing that we did last week, or could be. What other triangle would do that same thing, and where would it be? Would it be here? Because one of the sides would be negative there, right? Would it be here? Yes, because both sides would be negative here. So if I write that triangle down over there, it's the same triangle, right? The same triangle, except here we're going to have -3, -4, which will still give us 3/4. It's the same number of degrees here as here. In geometry, you'll learn that these are always the same, called vertical angles. So how do I figure out what 36.87 degrees is in that quadrant? We just did it a second ago. Add 180. So you're going to say this plus 180, and that'll give us our final answer. Now that's probably the most mysterious answer out of the 4 answers that we got. So let's check it and just make sure that it's working. So to check it, I'm going to plug it into the original, right? I'm going to go 4. To do tangent squared, you have to do an extra parenthesis. So 4 times tangent. You should be following along if you can. 4 times tangent. We'll try the weird one, right? Let's try 216. We'll just cut it at 0.8. All right, so we should get close then. And then I'm supposed to take that whole tangent and square it. And then we're supposed to go -7 tangent of our angle, which was 216.8 about. And then we were supposed to add 3, and we're supposed to get what if it's an answer?
0.
So 0 for this one. How come I didn't get exactly 0?
Because you shortened your...
I didn't put all those, I cut it at 0.8, right? But really close, it's clearly one of the right answers. Okay? If you want to check the other ones, you could, of course, just do a copy and paste. And real quick, go and try like 45 degrees was an answer we got, right? Let's try that one. Wow, when we put 45 degrees in, it came out as exactly 0. Why is that? Why didn't it have error this time? Because 45 was the exact answer, right? I cut that other one, I rounded it, so that's why. Okay, very good.